29 and 30 are just conceptual questions. Then the rest is multiple choice. And then the very last 2 pages are show work with some examples of horizontal and angled projectiles. Very similar to what kinds of questions you'll see on Monday's test on projectile motion. Okay. All right. Let me give you the answers to the homework that was due today. So, this up.
Wait, does the meeting care about safety?
It depends. Yep, just like my questions. They depend. You have to read the directions to the question to figure out whether you need to understand sig figs or not. But yes, it is a testable topic. Okay, so the answer in part A is 2.75 seconds for number 1, 2.75 seconds. In part B is 64.4 meters, and C is 9.29 meters. Number 2, A is 4.77 seconds. Part B is 64.4 meters, and part C is 27.9 meters. The answer in number 3A is 3.5 seconds, and the answer in part B is 60 meters. Number 4, part A is 57.7 meters, and part B is 10.1 meters. You want me to go over any of those before I give you the quiz, please? No, you have to pay attention to the sig figs in the question with the measurements that were given. Okay? Yep.
Is it when you divide and multiply to the least amount of safety?
Correct. Adding and subtracting is precision, decimal places. But multiplying and division are numbers of sig figs, least.
Can you do one A, please?
Sure. So first thing you have to do is make your sketch. Without the sketch, it's kind of hard to figure out what's going on. So we have a VI of 27.0 meters per second. You've got an angle of 30.0 degrees. There's the DX, the DY, and the T. You have to start by taking that VI at 30.0 degrees and finding the VIX and the VIY, which I'm showing you how to do here. These both have 3 significant digits, so you're going to stick with 3 sig figs. So that means the X component of VI is 23.4 meters per second, and the Y is 13.5 meters per second. This is all good? Okay. So in part A, I want the time. So when I look at my givens chart, I know that I've got my A's, I don't know the D's, I don't know the T's, and I have my VI's. I also know the VF at the top is 0 meters per second, which means when it lands on the ground, the VF would also be negative 13.5 meters per second, right? We have symmetry of motion in the vertical direction, which means that your VI and your VF are the same numerical magnitude value, but they are in opposite directions. So you could use that, or you could use VF at the top. So what I did here, looks like I used the VF at the final point, but let me do it the way I showed you yesterday. We're going to use it at the top and then double our answer for the time, which I think if you do that, you'll end up with 2.76 seconds. So I would still use VF equals VI plus AT, which means that T is VF minus VI over A. The VF at the top is 0. So when I plug in, I would have negative of positive 13.5 meters per second divided by negative 9.81 meter per second squared. And this is going to give me the time going up. So if I work that out, the time going up, 13.5 divided by 9.81, because those negatives are going to cancel, gives me 1.38 seconds, which means the hang time is twice that value, which gives you, I think, one slightly different answer than I gave you, 2.76 seconds for the hang time. Okay, and that's how you do part A. Anything else? Yep, Shannon. Part B of that. So in part B, we're looking for the range. In the X direction, the best equation to use is this one, where the acceleration is 0. So I'm going to take the X component of the initial velocity, which was found to be 23.4 meters per second, and multiply it by the hang time, 2.76 seconds. So 23.4 times 2.76 seconds gives us a range of 64.6 meters. Audrey?
Can you go part C?
So in part C, I want the vertical height. There's 3 different ways to get it. You can either use V bar is D over T, so D is V bar T, or you could use D is VIT plus 1/2 AT squared where nothing cancels out, or you could use VF squared is VI squared plus 2AD. Which way you want me to do it? This one? Okay. So to get the maximum height, I'm going to take the initial speed in the vertical direction, which is 13.5 meters per second. I'm going to multiply it by the time going up. Height is at the half time, the time up. So that would be 1.38 seconds. I'm going to add to that half of negative 9.81 meter per second squared times that 1.38 seconds, which would get squared. So now I'm going to just go ahead, go to the calculator, plug that in, 13.5 times 1.38 plus 0.5 times negative 9.81 times 1.38 squared, and that gives me an answer of 9.29 meters. If you use the full time of 2.76 seconds, you're going to get a dy of 0. And that should make sense, right? It starts on the ground, it ends on the ground. There's no displacement from launch to landing in the vertical direction. Khalees? If you're multiplying and dividing, yes. Anything else? Vince? 3A. All right. So in 3A, if I start with my sketch, it looks like this, where I've got my VI of 24.0 meters per second, my theta of 45 degrees. There's a DX, a DY, and a T. When I'm asking you in part A for how long it stays in the air, that means I'm looking for the hang time. All right. So first thing I did was I came up with my VIX and my VIY. So because my angles have 2 sig figs, I did those to 2 sig figs, 17 meters per second. 24.0 meters per second times cosine of 45 degrees is 17. Same thing with the sine of 45, 17 meters per second in the X and the Y. So if I make my chart, what do I know? In the X and the Y directions, I know my accelerations. I know my VIs. I know my VF at the top. I'm looking for the D values, and I'm also looking for my T values. These are all question marks. So part A says, how long does it stay in the air? It means I'm looking for the time T. The best way to do it is to use my vertical direction because the X values are not changing, so it makes it kind of hard to work it through. That means I'm going to use VF is VI plus AT. So T would be VF minus VI over A. The VF at the top is 0. So that means my time would be negative of positive 17 meters per second over negative 9.81 meter per second squared. 17 divided by 9.81 gives me a time going up of 1.7 seconds, which means the total time that I'm asking you for is double that, which is 3.4 seconds. And that's how part A is done. Anything else? Okay, then let's take our quiz. You may use your homework, your reference table, and your calculator to take the quiz. It is a show work question. Just follow the directions at the top of the page. Make sure you put your name on this, please. If you did not do the homework, you don't get to use the homework form. So put the packet away, but you can keep your reference table and your calculator out. I'm sorry?
I did 180.
I don't think you should. No. You either did it or you didn't. No gray area. You either did the whole thing or you didn't. Make sure your calculator is in degrees. If it's not, you're going to get answers that make no sense at all. And and you just have to use your reference table and your pencil or your calculator. When you finish the quiz, just let me know. I'll come pick it up. When you finish the quiz, please raise your hand. I'll come get it from you. Thank you. Everybody, one more minute to wrap it up. 1 minute. Thank you. All right, it is time to wrap this up. Let's make sure your name is on top of the quiz. And I'm going to come and collect it from you whether you're done or not. Time is up. Okay. So on that quiz, you had one calculation to do. If you were doing more than one calculation, you were doing it the wrong way. All you have to do is find the time. I gave you the x and y components of the initial speed. So you did not have to do anything with the angle given in the question.
Sorry.
All right, so now we're going to do a lab where we are going to shoot a projectile at an angle. Over on this side of the classroom, I have an angled projectile launcher. We're going to shoot that little red target that's on it. It's going to go out a certain distance. We are going to measure how far out it goes, and we're also going to measure the time it spends in the air. We're going to do that together as a class, and then you're going to work with a partner to answer the questions and do the calculations in the lab. Okay? I'm not going to do it with you. This is basically a review of angled projectiles. Here's the lab worksheet. When you get it, please put your name on it along with the lab number, which this is lab 12. So please put the lab number on the top. We're going to do this in pencil. Any crossouts on the page will result in a 0 for the lab. On a pencil with a good eraser. You and your partner are going to work on answering the questions as we go once we've collected the data together. If you and your partner finish it before the end of the period, great, you can turn it in. Otherwise, it is homework for tomorrow. Finish it with this. Okay. Let me shift over to my document camera again. This lab can be a little bit of a pain in the butt to get the data. So let's see. 12, yes. All right, so get your name on the top. And this is lab 12. All right, so here's what we can see we need to do over here in this data table is where we're going to populate the data. So when we populate the data, we'll be measuring the hang time and the range. We'll get the ranges at the end. And the way we're going to do it, I'll just show you how it's done. Right now, what I have here is this red target launched on here. And the way we launch it is we just click this or push down this gold lever, and you can see it goes out. Okay. Now it hit the floor and then slid. So what I'm going to do to try to help us figure out the ranges, on the ground, I do have a metric measuring tape already positioned. But what I'm going to do is put some paper in a big drop zone. And I'm going to create a drop zone here on the floor. And then I'm going to put some carbon paper over the top. So that way, when that projectile hits the carbon paper, it will leave an imprint. And then what we could do at the end is just measure from the 0 mark on the measuring tape out to each of those imprints. What we will have to do while these are being launched is measure the time. And as you saw here just a minute ago, I have a stopwatch here. So what we can do is get our times from the stopwatch. Someone will have to activate that. And then we'll just write down the times that we have for 3 times. Okay, does that make sense? It can be a little tricky because it doesn't always land in the same spot. So I'm just going to try to create a large drop zone here. I'm going to ask for your help because I'm still not 100% healed from my last surgery. Kara, can you come on up and help me out here, please? Miriam as well, come on down. I'm going to ask you ladies to create a very large area of white paper here on the floor. We're just going to put these down around this measuring tape. Just lay them out, okay, side by side, all till about here. And then, Miriam, I'm going to ask you to just put one little piece of tape on each of these like that so it doesn't move, okay? And while they're setting that up, and then once you have those taped, we'll put some carbon paper. Carbon paper just has ink on the back side. We're going to place that down so that way these, when they hit. Let's reset. Sydney, would you like to be my launcher? So come on up. I'm going to ask you in a minute. When we say go, you're going to hit that green gold button. So all you do is you just, yep. And all you're going to do is just reset like that. You're not going to touch this. Okay. So let me put, thank you. Go ahead, Miriam, keep going. A little piece of tape on each one. I'm going to place the carbon paper down. No, these will not be taken. Thank you, Miriam. Thanks, Karen. So we have a drop zone here on the ground. Hopefully it lands in this space. If it doesn't, and we have to go further, we'll have to get more paper down. We'll start with this. All right. So you ready for the first one? Okay, I'll tell you when to go. Ready, set, go. Did it hit in those? Okay, so that's one. So everybody, the first time that you're going to write down is 1.21 seconds. All right, let me reset this. Ready, set, go. Okay, there. Did it land in there? Yes. Okay. Just back to you. Whoops, sorry. So let's write that down that time, 1.36. And we have to do it one more time. You know how to recock it? Reload it? You good, Sydney? Okay, ready, set, go. Okay, let's write down that time, 1.23 seconds. Okay, now before we go on, now we're going to get our ranges. Thank you, Sydney. You're all set. Let's get our ranges here. Don't worry about the averages yet. Now we have to get our DXs written down. So let me pull up the carbon paper. Hopefully I see 3 marks where it hit. I see all three right here. 1, 2, 3. All right. So, Juan and Chaudhry, come on up. I'm going to help you read these off for the class. Okay. So, here's what we're going to do. You see there's a red mark here? What does that say? Okay. So, we're going to go out to the hundredths place, which is the nearest centimeter. So, this first one here, we're going to just come down. You see what number it is? 50. Well, we don't have to go that far, so we'll just say 59. So 2.59. Folks, the first one is 2.59. Don't worry about writing it down yet, guys. I'll have it up on the screen for you to get in a minute. Now, we have to get the second one. Down. 68, okay. So 2.68. And what's that last one? 2.
Oh, no, the second one's going to be 2.67. Yeah. The other one's going to be 2.68.
Okay, we'll just make this last one 6.7. Very good. Thanks, guys. All right. Now, what I want you all to do is go ahead and average those numbers for the times and the ranges. Remember, your averages should have the same precision as the data itself. So that means you're going to write down your averages to what decimal place?
100.
The hundredths place. Very good. All right. So what are we getting for the average time? 1.27. Okay. And what is the average range out to the hundredths place? Okay. Do you all agree with those numbers? Okay. Now, here's what we're going to do. You're going to take these averages for the time and the range and put them over here. So the average time is 1.27 seconds. The average range is 2.65 meters. Now, I want you to think about this for a minute. We didn't measure the height. This refers to the total vertical displacement from the launch to the landing. How far did it change its vertical position from launch to landing? What was that vertical change in position? Yes, you do. You should know. 0, because it started on the ground and it ended on the ground. It did not change its vertical position from launch to landing. Okay, so now I want you to go ahead and work with a partner to answer these questions. If it says calculate, you're going to use, you can make your table and use the same table for the whole thing if you want, but you're going to make sure you show an equation. Let me write these steps here for you. You need to make sure anytime it says calculate that you show me an equation, if necessary, algebraic manipulation to get to the final equation, then your substitution with units, and then of course you need answers with units and sig figs. Okay, those are the things I need to say whenever it says calculate. All right? Good luck.
Thank you.
You can work with a partner to help you work out these questions. If you want to make a table like we usually do, you certainly can do that, what you know about the X and Y directions. As you answer the questions, those things will help you populate your table. Okay? And of course, you have these as well. This pencil sticks. The only thing this table gives you is this. This will be hard to do if you're not working with a partner, so I would strongly suggest you work with a partner to help you figure this out. Are we already stuck? No? Okay. Gavin, I want you to take your watch off and put it in your backpack. You're not allowed to have smartwatches at school. If you're going to wear a watch, it's got to be a dumb watch without internet connection.